Okay, so today we're going to start talking about functors and applicatives, which are like sort of the first two steps to monads and I/O. So monads are next week. That's like the big crescendo of the course, right? That everyone is going to learn what a monad is. It's not going to be that difficult. Oh, right. What I meant to say is next time that we get together. So that's actually a good point. Next Tuesday is Monday. And next Monday is Tuesday, which is a holiday. So functionally speaking, that means we're not meeting next Tuesday. Everyone get that? But you are to show up to your Monday courses next Tuesday. Okay. It's kind of confusing. As a side note, like I realized I got totally screwed by like having a toddler in daycare on Mondays. There seem to be a lot of Monday holidays. And I still have to pay, right, for my toddler not to be in daycare because it's a holiday. And that doesn't mean I get to have a holiday. That just means that I lose a day to childcare. I also wrote your exam. It's submitted, so it's very similar to last year's exam in shape, except I sort of deleted one long answer question and made it like two short answer questions. So it's 10 very short answer questions, and I think 8 short answer and 1 long answer. So you should be able to find the Comp 3400 exam from last year on the library. I don't know if you've taken a look at it yet, which puts you at an advantage because last year, I had no previous stuff for students to practice with. I would say it's like maybe a little bit more difficult than last year because I think last year I made it way too easy. I had to submit it really early, and like I really hadn't even fully fleshed out the course at that point, so I was too afraid to put anything on it that was too difficult. But I don't know, maybe it's 5 to 10% more difficult than the year before. And there's more of an emphasis on functors and applicatives than there was last year. So you should pay attention to this class. Yes. Oh, I did put a lambda calculus question on it. There's one short and one, so there's one very short question and one short question. And they're like throwaways, right? If you did your homework, they should really be slow balls. There's some hard stuff, but just remember, like, you don't need to solve it all and skip stuff that you can't solve. Because the nature of this course, like, I don't know if you're like noticing this, but it's like pretty hard to get partial marks. Right? It's either like totally correct, or in terms of like your programming in your Haskell, it's like either totally correct or totally wrong. The long answer question is a induction question, so you're gonna have to do yes, the mathematicians are cheering. But remember, I'm going to be pretty savage in my evaluation of them, so I expect them to be done quite well. Especially by that time, you would have submitted at least 3 inductions by then. So I expect your inductions for this assignment to be much better than the last ones.
What was the average marks for the induction question?
Poor. I think like maybe 6. Because you could get 4 marks just by like discovering the magic step of rotating and connecting. I wrote up a big long note about what was mostly done wrong. So please correct your inductions for this time around. There should be much less mistakes done now that you know that what was missing. Okay, so again, this lecture is being recorded, and today we're going to start working on functors and applicatives. So the material may be getting a tad heavy, so I'm going to try to go like much slower than I normally go. And like feel free to like stop and ask questions because this can be kind of confusing, although it's sort of like ultimately simple. So if you recall what we were doing sort of last week and the weeks before, Haskell's about like finding patterns and then sort of like generalizing those patterns. Right? So on the first assignment, I gave you this magic function. I had you implement 3 functions that had a similar pattern, and you basically discovered fold, which is sort of a higher level function. We also have map and zip, and using these we can like simplify our programs. Now, what I want to do is keep generalizing, right? So I want to generalize the notion of map itself to beyond just lists. Now, if you look here, so here's how the list map worked. You give me a function from A to B, you give me a list over A, and I give you a list over B. Now the thing I want you to understand or notice here is that the function, like what map is doing, is just sort of adjusting or mapping the inside of structure while leaving the outside structure alone. Like if you were to map over a list, you can't really change the list's length in that mapping. So in some sense, like a list map is what we call a structure preserving operation. Functors are like the generalization of this idea, right? That we can have, that maps should really be a collection of higher order functions that do structure preserving operations on things, like map does. Can you think of any other structures for which we would like or should be able to define structure preserving operations? Like what other structures do we have? Yes?
The identity function.
That's not a structure, that's a function, right?
You just said function has a structure, so.
No, I'm saying list is a structure. Mapping F over that list leaves that structure invariant, right? So a map takes like lists to lists. It only changes the inside. Yes? So that's another function. Sort? What's the structure then that it's leaving invariant? Oh, I see. Maybe I have to ask a more clear question. Like, give me an example of another structure that's not a list. Tree, right? So maybe we want to like go into a tree and like increment every node by 1, right? That would be a structure preserving operation because the tree would be the same tree afterwards. The inside of the tree would just change. What other kind of structures do we have? That's a list essentially, so technically correct. Anything else? Yeah. Tuples, yeah. Maybe someone can figure out another one. Maybe. Maybe, yeah. That's the one I want to work with. So we have this maybe data type. Recall that's what we use in case a function can fail. So what's the structure of maybe? Like it's a just, right? So you may have like just 1. Now suppose we want to increment just 1 to 2, right? We may want to say map +1 to just, right? And the inside of just will change, but the structure itself is going to remain invariant. Okay, so we're going to switch from using map to like fmap. So map is so-called because it only works on lists. Fmap is the map that is like the functor map. It's the map that's like will work generally on any structure. So map is a subset of fmap. Anything that you can map, you can fmap, but not the converse. So here's how we define sort of mapping over a maybe type. So here we have fmap, which looks very similar to map, but in this case, it goes from A to B, and it takes maybe A to maybe B. So I can say fmap greater than 0 over just of 1, and it's going to change it to just of true. I can say fmap over the tuple. That was another suggestion for structure preservation. So I can say fmap equal to 2 over this tuple, and it goes 1 to true. So you have to...
So are we defining fmap every single time?
So these are built in at the moment.
But if they're built in, how are the types different?
Because the type itself is generic, right? I'm just utilizing them specifically in the... I'm saying once you fmap over a just, it's going to have that type.
Yeah, okay.
Although, yeah, like you're allowed to be confused. Maybe that was a little bit confusing. So let me just go in. I'll show you the type of fmap. Okay, so the type of fmap is it's an instance of something that's a functor. So we're going to talk about what it means to be a functor, but essentially it just means you've defined fmap for the type. And it's just this, right? Give me a function that takes A to B, and give me something with structure over A, and I'm going to return something with structure over B. But the structure is going to be the same structure. So those are just the patterns that sort of are sort of, what's the word here? Well, anyways, it's the same type. It's just specialized to the types that we're using. So notice here, though, like what did the functor do over tuples? Like it didn't do anything to the first one. or it only did something to the second one. So it's kind of weird, right? So you're going to have to look up, or like you may not get the behavior you want over with a map on the default functor. We could easily define another functor which like changes the first position rather than the last position. That would be a different functor. Here it is one for a tree. So suppose I just spin up like a basic binary tree with nodes that have values and leaves that have values. Then I can define an fmap. That's a function that goes from A to B that takes a tree A to a tree B. And again, the thing that is important is that the structure is the same over both. And I can say fmap over this tree, and it will go into the tree and increment all the nodes by 1. Right? So you should see now, or like start to think, geez, this could have saved me a lot of work, on previous assignments, especially when you're working with like the maybe data type, because you might want to like go inside without doing a pattern match. Okay, so what is the common pattern here? So I want to map a function a to b from maybe a to maybe b. I want to map sort of a tuple, this function to this tuple to this tuple. Now I want to unpack this a bit to show you why it's only changing the second position. You can write this tuple as like this. So like this is a constructor that generates tuples whose first position is A. So that's like the structure that's invariant from like that second thing to that third thing, this. Right, so that's an explanation of why the first position isn't changing, because that first position is part of the structure. Right, so maybe this line is a little bit sort of more clear than this line, why only the second thing is changing. Right, because again, this is the structure. So the generalized pattern here that we already looked at is you have to give me a function from A to B, then you have to give me A with some structure over it, and then I'm going to be able to give you B with some structure over it. And this, I'm going to keep repeating this over and over again, but the fact that this is structure preserving is the whole point of defining these fmaps, or these functors. Oh, we have something in the chat. Maybe. Oh. Okay, so recall type, or a type, is an instance of a class when it provides the operations that define the class. So you've probably, I don't think I've actually officially asked you to define custom instances, but we've defined some custom data types, and we've defined like special orderings over them. We've shown how to show those things. So we have defined some custom classes. A functor is just a data type which provides this fmap. That's it. Right? The same way that in order to be an instance of order, all you need to do is define ordering, or to be an instance of numbers, you have to define adding. And so again, in order to be an instance of a functor, you need to provide an fmap. Right? So this is what you're going to have to define. You're going to have to define some fmap that takes a function a to b, that gives you some structure over a, and then that same structure over b. That's all that's required to become an instance of a functor. So we'll do this, except that you have to satisfy these two rules. Right? There's a lot of things that will type to this that are not going to be functors. So the functor rules are as such. If I fmap the identity over f of a, nothing should change. Right? Going into the interior of the structure and mapping the identity, right, should leave the outer structure and inner structure untouched. If I fmap a function composition, that should be equal to the function compositions of the fmaps. It's sort of like fmap distributes over function composition. So how do you think we're going to prove these two things? Yeah. What's a fast way to check it, though? What's a piece of technology I gave you?
Quick check.
Yeah, quick. Like, this is pretty much why quick check was created. Right? Because these functors, applicatives, monads, they're all going to have rules that you have to satisfy. And these rules are all going to be properties. And running them through a quick check should give you sort of initial confidence that the thing that you actually wrote is in fact a functor, applicative, or a monad. Okay, so here's something that we can define that we've seen already. So let's just define the regular functor over lists, right? Which is basically just fmap. So we would do it like this. We would say, so the instance of functor for list, and remember that's the syntactic sugar for the list constructor. Now, this is commented out, and it has to be commented out. You're not allowed to have type definitions in functors. it is still nonetheless good practice to include it here. So I'd like you to include these type definitions as comments when you're defining your functor instances. But otherwise, you should just let the typing system do its thing. So what does it mean to define a functor over lists or to define mapping over lists? Well, fmap of anything over the empty list is empty. Fmap of f over x cons x is fx cons fmap f over x's. Right? This is the sort of the very basic map that we've been using the whole time. So let's just see. So this will indeed work in Haskell. If I say fmap plus 1 over the list, you can use it instead of map. If I say fmap greater than 1, 1, 2, 3, I get false, true, true, right? So here I want to emphasize that, yeah, look, we've really jumped domains. Like the inside of this structure has changed, but the outside structure is the same, right? They're both lists. They're both lists of length 3, right? Despite the stuff on the inside changing. If your length of the list changed, you haven't defined a functor. Could we define an fmap so that like the thing that we get is longer? Sure, we just have to like, I don't know, do 2 of those, but then that wouldn't be a functor anymore. So just be careful. You can indeed define functors that will type properly, that nonetheless will fail to satisfy the properties. That was on the exam last year, actually. I said, give me an example of a functor that types properly, that's nonetheless will fail the functor rules, and then show me an example of how it fails. Okay, so here are the functor rules again, and this time I'm going to give it using the infix notation, because somehow when proving I find it easier to use the infix notation. So you may have seen this functor notation with the $sign. There are plenty of submissions for permute that used it, for example. Now you know what it does. It's basically the infix map operator, right? So I can say +1 map over this list, and you get 2, 3, 4. Why do you think we chose this notation? Like, what's the $sign normally used for? Apply. Yeah, apply. So this is basically saying, like, do a map apply. Like, apply this, but, like, over the whole structure. So it was, like, a deliberately chosen piece of notation. I can also say greater than 1. Like, map this to 1, 2, 3. And you get false, true, true. And I can also say greater than 1. Sort of functor applied to just 1, and you get just false, right? Because 1 isn't greater than 1. So this fmap has sort of, it's a function that's now going to let you map over anything that has structure, not just lists. So all the things that you used to do for lists, you should now think of doing for anything, right? Anything, any data type that I give you. You could even define a functor for like those polynomials that I gave you. I wouldn't know what it would do, but like I could say, define me a functor that, you know, increases the degree of this polynomial by 1, right? And you should be able to do that with a map. How do we prove if a functor satisfies the functor rules? Well, so I'm just going to restate them. Fmap of the identity function needs to be the identity function. So this looks confusing because it's in the point-free form, I guess. But this really means that if I give number 1 x's should come out. And then again, that function composition, fmap distributes over that. So another way of looking at it is like this. This is the infix form for those functor rules. So sort of mapping the identity gives you the identity, and then distributing this composition over the functor will distribute like this. So again, I prefer the infix style when proving, although you can't use the infix style when defining the functor to begin with. You have to define the functor with this fmap. Okay, so we said we needed induction to prove some of these things, but I have to teach you sort of a different type of induction, because the induction we've been using has been sort of like mapping the natural numbers to a predicate. Now I need to teach you something called structural induction. It's like basically the same induction that you've been using. We just need we need some tweaks, right? Because the domain we're moving from now is not the natural numbers, but like all lists, or like all maybes, or all trees, right? So how you work with structural induction is follows. So you have some recursively defined structure, which is basically any data type that you can define in Haskell, like even recursive ones. To be a recursively defined structure means there's the rules for inclusion are like recursively generated. Like you're a list if your head is from the list type and the rest of you is a list. Right? You can always apply recursive rules to determine inclusion in the set or not. All of these things that are recursively defined therefore have substructure. Right? So trees have subtrees. Right? Lists have tails. My polynomials had smaller polynomials that they're built up by. So given some structure with some substructure and some minimum structure. So minimum structures, like what's the smallest list? Empty list. What's the smallest tree? Well, it depends how you defined it. It's either going to be empty or like a tree with one node. What's the smallest monomial? Or what's the smallest polynomial? I guess that's a single monomial. So this is kind of different, right? Because the minimum substructure can be like an infinite set of stuff. Like there's an infinite amount of trees of one node, for example. So the base cases are going to be a little bit more complicated because your base case is going to have to prove like an infinite amount of base cases. But it's going to be okay because we're just going to use sort of like a variable to indicate that we're using something arbitrary. Okay, so again, suppose you have some S. It's a recursively defined structure, as in some data type that we've defined in Haskell. This structure has substructure, and the structure can be partially ordered somehow. Partial order just means that given two things, you have to be able to tell if they're less than, greater than, or the same. But you don't have to, they don't have to be totally ordered. So list length is a partial ordering. Like the list of length 2 is less than the list of length 3, and equal in order to all of the lists of length 2. If you it's like sort of like a lattice instead of like a list. So it's like you have all the lists of length 0, then all of the list of length 1 and length 2. Right? So as long as you can like sort of enumerate them like that, then you can use structural induction. This is just giving us a way to like be able to make very sure that when we're like calling substructure, that substructure is somehow smaller in the ordering, right? Because we need to keep inducing until we hit like the base case. So the substructures better be smaller somehow, and then their substructures better be smaller, and then that whole chain better hit the base case. So structural induction implies, so these are the two things you have to show true. If P is true for all minimum structures, so again, empty list, trees of length 1, monomials, and Px prime is true for x prime any immediate substructure of x, then Px is true as well. This is very similar to induction. So maybe in your previous inductions you've been assuming n to deduce n plus 1. Here you're going to sort of have to assume, if you have Px, you have to assume Px is true for all substructures of x. So I'm going to do a real example so it will make it much more clear. Okay, so for your homework, I want you to prove that the list functor satisfies the first functor rule. This is going to be trivial because it's just the identity. What we're going to do now is prove that the list functor satisfies the second functor rule, as in you get this distribution of g.h over x's. So let's do this now. Okay, I'm going to give you a set of assertions that I'm going to allow you to use in your homework. Because remember, whenever you make an assumption, I just want you to make it very clear. And for these types of proofs in particular, I want you to be very careful. I want every single line that you write to be justified somehow. Not for me, but it prevents you from making mistakes. Okay, so these are the only things we're going to use in our proof. I'm going to use the definition of the functor at play, right? So we're doing a proof over the list functor, so I'm going to have to utilize the definition of the list functor. I always include numbers, and when I include numbers, I want you to cite these line numbers in your proof, not your own line numbers, just so it makes the marking a little bit easier. Even on your exam, I put numbers there. So on your exam, you should utilize the numbers on the exam. Okay, so these are the things I would like to take for granted. The evaluation order of composition, we're just going to take for granted. Like I want to take for granted that f composite g of x is the same thing as f composite g apply x is the same as f applied to g of x is the same as f applied to g applied to x. So does everyone just at least agree that they should be equal? that if I were to type this into Haskell, they're all going to be given the same things. All that's happening here is it's moving the evaluation order, right? Saying evaluate this first, evaluate this last, which becomes relevant. Another way of thinking about this, it's like sort of saying like this should be associative, like no matter which way I sort of bracket it, it should always give me the same thing. Okay, this is something that may be confusing. So I want you to ask me a lot of questions about this. So in our proofs, we're going to have like a chain of equalities, and we go like top down, right? But they're equalities, so we should also be able to go bottom up. Like it should make sense in both directions. When we move top down, we're doing applications, but we may sometimes want to do a unapplication, which would sort of be an application in the reverse direction. So application down is equal to unapplication down is equal to application up. And application down is equal to unapplication up. Okay, so this is I want to be able to say this, right? Suppose I have a function, and all that function does is increment something. I want to be able to say, I can deduce 3 from f of 2, right? F of 2 is equal to 3. That's the easy one, right? If I give 2 to f, you get 3. Okay, but there's an equality in there, right? F of 2 is equal to 3. That means I should also be allowed to take 3 and replace 3 with f of 2. Does that make sense? So to say I get 3 from f of 2 is to apply f. And to say I get f of 2 from 3 is to unapply f. It's to recover f from its evaluation. Because again, right, when we have f of 2 is equal to 3, it's an equal. I should be able to go in both directions. So just keep this in mind, because this is the main mechanism by which you're going to like do proofs, right? Because all you're able to do is use definitions of the functor itself and these application of composition, and this is how we're going to do it, by basically doing very smart unapplications to like make stuff appear again. So I have 2 proofs that we're going to go through, and please stop me, otherwise we may be a little bit short today. Okay, so here's our proposition, and the proposition looks a little bit different now, because it's not a proposition taking natural numbers to some predicate statement. This is now a proposition taking something of structure and making an assertion over it. So I'm going to say, for any x's of type list of A, we have, and here's my proposition, P of x's, if and only if, and that's the functor rule too. Right? That's the thing that we have to prove is true for every x's that we have. So is people okay with that statement? Okay, really, you have to stop me today at any point I say something confusing, because we may get down a rabbit hole which may be hard to climb out of again. Okay, so again, P of a list is true if and only if I can distribute this computation, map that over the list if that's equal to the distribution of the individual maps over that list. So what's the first thing we do in induction? What's the base case in this case? What's the minimum structure among lists? How many empty lists are there? Okay, so this one is good, right? We only have one empty list we have to deal with. So here's the base case. So I need to show that g.h mapped to the empty list is g mapped composite h map to the empty list. Agree? So let's do that. So what's like the only thing I can do here at line 1? I just have to apply the definition of map. So what's the definition of map over the empty list? Empty list, right there. That's all we had to do here. So I just applied g.h to this. Now what do I do? It seems like we're sort of stuck.
The right-hand side.
Huh?
We consider the right-hand side of the preposition, like the equals.
Oh, yeah, but that's like that's true for like rough work, right? So you try to make your way, you start at the bottom and try working your way up, right? Like I have to make this empty list equal to that, right? But how do I do that? Like you're probably saying evaluate empty list and then you're going to get empty list. That's one way of doing it, but it's more elegant. Like I need to show that this is equal to right-hand side. So there should be a sequence of equalities that get me to the right-hand side here.
On
unapply. That's exactly why I gave unapply, right? Because if we were doing what you suggested, which is valid, and that's how you would find out the solution. You take the right-hand side and you reduce it to 0. And then you'd probably take the left-hand side and reduce it to 0 as well and say that's great. But that's sort of like that's more amateurish than you would do in like actual mathematical literature. Because you've like reduced two things to 0. But like, you know, that means you can get from one to the other. So I want to see that all in one deduction. Okay, so what do we unapply here? Not H. I'm trying to recover these, right? So this is like mapping H to something, and this is mapping G to something. We don't have H, we don't have G. Oh, you mean map? Map? Like this? Great. Okay, that's exactly what I want. So I'm saying unapply G.
Oh, I said unapply H.
That would have also worked. It also works, depending like if you're doing on the inside or out, right? Both work, right? Because, and you have to be careful. You don't unapply G or unapply H. We're unapplying G map, and we're unapplying H map, right? Unapplying G would be G empty list. Okay, so yeah, like if I map anything to the empty list and get the empty list, then from the empty list I can unapply a map, and that's fine. And then I can unapply the next map, and that's fine. And then I can use the composition rules to like get the dot where I need it to be. And then have we shown like the left-hand side is equal to the right-hand side of equation 1? Yes, for empty list. Okay, so that should prove the base case, right? Any questions there? That was just the base case. I'm like, that's what I'm saying. Things are going to get a little bit hairy, right? Because if this is the base case, right, we haven't even touched, like this is the trivial case, right? But it is trivial. Like I'm saying, if you map something to the empty list, you're going to get the empty list. And therefore, I can like unapply as many times from the empty list as I want, right? Okay, so yeah, savvy? Okay, we move on. Okay, so here now is the induction step, the harder step. So I'm just going to rewrite this. So one thing I want everyone to correct in their next inductions is being less repetitive. It's okay and most appropriate to just say assume PX's. Right? If you asserted a P, you don't have to keep repeating yourself. Right? So I only put this here because I'm working on slides. Right? And we sort of need to be able to see the statement in order to work with it. So just keep that in mind when using my slides as a framework, that like some of it is there because I'm constrained by slides. Remind me to release assignment 1 solutions. I have them. Okay, so here's the induction hypothesis. So I'm just going to assume PX's, which is this statement, is true. And I want to consider sort of PX con X's, like the next one up. Right? Because I'm saying in order to prove something for a list of length n plus 1, assume all lists length n satisfy this property already. Does that make sense? So like all substructures of x con x's are x's. Right? All possible tails of x con x's. Okay, it may take some time to grapple with this, but essentially that's what I'm trying to say. Like if you have a list of length n plus 1, assume this proposition is true for all lists of length strictly less than n plus 1. This is what structural induction means. We're like assuming an infinite amount of stuff behind us, not just exactly one proposition. So let's move here. So first step, what's the only thing I'm able to do here? Yeah, the only thing I can do here is apply the definition of what the functor means in this case. Does anyone remember what it means to map over x con x's? Yeah. It's applying g dot h to x. Well, it makes a difference. You're not mapping to a scalar. So that's correct. You're applying g dot h to x, cons, and then the rest of the map. And then here, like I'm just going to specify what I did. Right? You really do need to justify your steps because it may not be as obvious to the marker what you have done when you're doing it, especially when you're unapplying stuff, because that can seem kind of magical. And it'll ensure that your work isn't wrong. That's like the other reason to do it. Okay, what now? Right, we're trying to get to here. Right? Use the induction, right? The induction has appeared. Where is it? Here, right? Okay, so I've assumed that this can be replaced with this. Okay? And notice here how I'm explicitly invoking the induction hypothesis. It's another criticism I have of some of the inductions. Not just enough to assume it. You have to like use it explicitly. And if you haven't, that's a big sign of trouble. Okay, what next? So we got this. Now we sort of have to like unroll everything, right? Because I need to get sort of my x back over there. How am I going to do that?
I have to say that G dot H kind of means the same as implying the functor.
No, so like you can't like start making really flighty arguments like this. Because in the end, I'm going to say what one operation, application, or definition did you do to go from that line to the next one?
You have to use something with cons.
Composition rules, right? I want to like sort of unwrap this and this, right? Just to like separate everything out a bit. It takes some practice to do this. Because what you're effectively doing is like simplifying Haskell code. Right? This may seem bizarre that like we're working with Haskell code the same way that we'd work with like a mathematical expression. I like it. I think it's kind of cool doing stuff like this. Okay, so there's my composition rules. After this, I'm going to unapply G. Right? Because if you look at this, what do we have? We have G applied to this, and then G map applied to that. Right? So that's like applying G map to this.
Could you explain that? Okay. Slide.
Yep, that's no problem. So again, so remember what a map is in its most primitive form. Like map f to x con x's is fx cons map f to x's. And I'm saying that's exactly what this is. This is what you get if you if you map G to the mapping of H over X's. Right, so again, so here's G, the thing I'm going to map. So there's the cons, right? And then there's the G map, right? So if this was like, this is the list we're mapping over, right? And then there's its head. Okay, so that's what this list is. Yes. Exactly. Right. So now if you look at this, this is like applying, this is like mapping H to x con x's.
If we unapplied G map, then why is G map still in that line?
It's like discovering G-map from
Well, you mean why is it still like it's here and then why is it here?
Yeah, that point there.
This is the one that disappears though. So again, if you have, like I knew this would be confusing. It's confusing every year. Okay, so you have map G to x con x's. And I'm saying that this is equal to gx cons map G x's. Yeah?
Yep.
Or I can say, maybe I should do this. G mapped to x con x's is equal to gx cons G this to x's. Yeah. So I'm saying actually in this case, imagine x con x's was actually like what you get if you map H to like y cons y's. Right? This would be something like hy and then H map y's. Right? So I'm saying like we're exactly in like this position where this is hy and this is this. Oh, and then this has to be it's going to take some time staring at this. Yeah, I don't. If you just replace in your mind this hx with like x and x's, it will make sense. I think it's just the tie up here is that like I've already mapped h to the list, right? And then I'm unapplying g from that, g map from that.
Okay.
Do all of you not understand? Are there some people who understand? How many have I lost? We're good? All right, sorry, mate, you've been outvoted, right? But yeah, just, you'll have to work it out for yourself, I reckon, or, yes.
So it's probably a little bit like picky, but why did we define, so we specifically defined how application works, how the composition rules go.
Yeah.
But we never specified how the composition, like the colon actually interacts with our function.
This colon?
Yeah. So I understand that it is just semantic sugar for like building lists. But if we defined all the other things at the start of the proof, why don't we have to define that one? And like how it interacts with our function.
Well, I suppose that like cons operation like is at play here because it's inside the fmap definition. Like we're pattern matching out of it. Like fmap is gonna, like map is gonna have to do a pattern match, right? The recursive step is going to be map f of x cons x, right? Let's go back. Here, right? Here. So, like, I wouldn't even know how to define that. That's sort of like, as you said, syntactic sugar. Like, we could remove it. We could add the cons operator. But essentially what I'm saying is that's just a pattern match. There's not really much you have to say there. Yeah. Okay, so where were we here? Okay, let's keep going, though. Okay, so we unapplied our G. We unapplied our H. Now what? Are we done? Yeah, got to use the composition rule to get that dot there. And then once we have that, and we're done. Right? And thereby p x cons x is, what am I missing? What's the last thing I need to do? Conclude. All right, those are the, don't forget to conclude. That's an easy mark, right? Oh, and you have to state that you're using the principle of mathematical induction. Because that's the theorem by which this whole thing works.
Do we not have to say, like, structural induction or strong induction?
I don't know, I'll ask the mathematician. Does structural induction fall within PMI?
Depends on if your definition of induction is over any level of the set, then that is the principle of mathematical.
I would say that structural induction falls within PMI.
You're the one marking.
I'm the one marking, so yeah, I guess I'm the only thing that matters. Okay, but there you go. There's this is a functor proof for the easiest functor. It's going to take some time to look at it. These unapplies get really, yeah, can be confusing. But we're going to do more examples and to flesh this out. Okay, so this is, let's write now, like let's shift gears from like proving something to like actually writing a new fmap on a new data type that we create, right? Because so far, all we were using were like the built-in functors and maps. Like what happens if we have a new data type and we want to map over that? So here's a visual example which will perhaps emphasize the fact that this is a structure-preserving operation, right? Like I may want to say map greater than 2 over this tree to get a tree that has the exact same structure that has true and false inside. And when I say exact same structure, I don't mean I went from a tree to a tree. That's not structure preserving. I have to go from like a tree to like the exact same tree, right? If I were to like count the number of left and right children in every node, that has to be the same for both, right? That's why I keep saying structure. The whole structure has to be, only the inside can change, which is going to be super important when we start talking about state transformations and monads. Okay, so here's like the common, so I hope by this point, if I say write a custom data type to like represent a tree with values in its nodes, everyone would be able to do that. Is this a valid tree definition? I need an empty tree in here, don't I? Or at least a leaf. Do I?
Because the simplest tree is one node, and you've got node.
Well, how do I get a tree of 3 nodes? Oh, I guess that's just a tree. Oh, yeah. It's node is leaf, essentially. Node is, I should have called it leaf. That's why I'm getting confused. Right? This should be called, like, this will work, technically speaking. With
Actually, how did you get a tree of two?
Right, I probably should have included empty in here. Or maybe I can't have, like, there's nothing stopping me from creating this data type. It's still a data type, it's still going to do stuff. This may only be able to produce balanced binary trees, and this should still be called leaf. Okay, I'll correct this, but for now we have an example where I've created kind of a really dumb data structure which is only able to hold balanced binary trees, but that's fine. So let's see if we can define an fmap over all balanced binary trees. So this would be the obvious way of doing it. Should I try this in the REPL? Okay, let's try it in. Or maybe we can like try to correct it. You want to try correct, like writing a functor for a proper tree, but you guys have to try to help me. Tree.hs. Okay, so let's create a real tree. Data for a tree of A. So that should be something like empty, or a tree of tree, or maybe I'll call this node of tree A, tree A. You think that's going to work? Let's load her in. Okay, and I always forget. So we need to define this now. Okay, so we can build trees. Now we have to define an instance of functor for this tree where fmap is going to do this. So what is the obvious way to like map over this tree? What should we map to empty? Oh, I guess we need our fmap of anything to empty is just going to be empty. What about fmap of f to, I got to do a pattern match, node, tree left, x, tree right.
fmap f to t tree left, and then f to x, and then map f.
Tree right. Okay, so that should get us the functor. So let's get a tree, I don't know, 3 nodes. So this is a node with node 1, 2, node 3. I didn't derive show. Oh, and I can't call it that. Ah. What did I do wrong?
Your node needs three not arguments, but your node, you can't do node one, right? You need to do node empty, one empty.
Oh, right. That's not a leaf. Yeah. Thank you. Perfect. Okay, so we should be able to see that. And now I should be able to, okay, let's just ask which one of these are greater than 1. And I can, or use the infix over that. Yeah. Okay, so we've defined a custom data type, we've defined a functor over that data type, and we've used it. Okay? But again, nothing is preventing us from creating that like functors that aren't going to work. Right? I could have said this is going to go to empty. We can like do this whole thing again. Right? Is that structure preserving? No. Right? Because I started with a tree of like 3 nodes, and now I have a tree of 0 nodes. Okay, so just be careful about that. You can write functors that type properly, but nonetheless aren't functors.
So does the functor keyword, do they not check whether or not it's a functor? Like when you write instance functor tree.
It will check that it has the correct type. But can it check that it's a functor? Even if we wanted to, would we be able to check that it was a functor?
If you could do that for any case, then it would be able to like detect if the functions equal for all values, which is like IQ of proving.
We can't automatically prove stuff. That's pretty difficult, right? You can quick check, right?
To the tree, you can do like a pattern match to see that it's the same tree in structure, right? Surely you can pattern match that away.
You can't get Haskell to automate proofs. Well, you can, but it's tough. You can do quick checks, which give you like confidence, right? That if you pass your quick checks, you should be like, this is probably a functor. And it will prevent you from, it will catch you if you define something that isn't a functor. But no, we can't have Haskell check that it satisfies all those rules. Right? Automated proving is not easy. Okay, so we do not and cannot include a type signature, this thing, but I want you to anyways as a comment. It's good practice. And we must define fmap. You can't define fmap using the infix notation. You have to use the prefix notation. But as soon as you define this fmap, then you can automatically use the infix notation. So keep that in mind. Oh, so yeah, this is the confusing part. You can use the infix fmap to define the prefix fmap. So the prefix, the infix stuff can show on the right-hand side, but not on the left-hand side. If this confuses you, just don't use the infix notation. Yeah.
I use the apply ones on the left-hand side. It complained that you can't actually use the apply symbol, but you can use it on the right-hand side in the same way as this is happening.
Yeah, this is probably why. Can't sort of do.
Haskell not allow.
It's probably something to do with like the inability to pattern match out of it and stuff like that. I don't know. Sometimes Haskell does mysterious things, and we just have to follow it. Okay, so here's some examples of applying our tree functor. So here's a tree. I'm going to double all of the nodes. I'm going to do this just to show you that you can move domains. Now, to your question. Oh, yes, sir.
Before you said we shouldn't define the type signature for our fmaps, and we should leave it to the type engine. What type did it give our fmap for our tree then? Is it something we wouldn't be able to write by hand?
No, this would be A to B, tree A to tree B.
Okay.
Yeah.
So you just let the type engine do it?
Yeah, it's better. In fact, if you put this here, Haskell will say, don't like remove it. I'm not moving until that's gone. But somehow it's better to have it there, especially when. No, if I remove this comment, the Haskell would say you can't take it out.
Oh, why does it take that?
I don't know. Again, sometimes Haskell is mysterious. It just wants the type inference engine to do its stuff. But if you look in Hutton's book, for example, this is common practice to include the type signature as a comment.
You can't have two type signatures for the same function, right? And the fmap probably has a type signature somewhere else in the tree.
Sure. I don't know. I don't want to say anything because I genuinely don't know the answer. If you find out, you can let me know what's the reason. But again, Haskell does a lot of stuff that sometimes don't make sense to me, to be totally honest with you. So there's our tree functor. Have we defined a functor? Probably, but answering requires proof. So you want to go through and define that this tree functor satisfies the functor laws. Oh, here I seem to have defined a tree properly. No, yes? No, something's wrong here. Okay, I did have like a big long. Okay, I'll have to fix this data type later. This is odd because this was from last year's homework, but it may be a balanced tree. But I'm sort of running out of time for this one. But let's do the base case for this one because the base case is different than the base case we did before because there's an infinite amount of base cases. So let's demonstrate that this tree functor satisfies the functor laws. And we'll do which functor law are we proving here? The complicated one, not the one of mapping identity over identity. So let's just do the base case. So first I have to state the proposition. And to be entirely correct, you would probably have to write this down. But in your work, just say like import it from the assignment. right? Like let T be a tree of A and fmap be given by page 1 of the assignment statement. Like that's fine. And use the same numbers that I put there, or just put it there if you want. Then this is our proposition. Right? The proposition on this tree is true if and only if mapping the composition of G and H to the tree is the same thing as applying the F map of G composed with the F map of H to the tree. Okay, so here's the base case, and here's where it's a little bit different. What is the minimum substructure of this type of tree? And I guess that's why I didn't include empty for this one. I want to prohibit having empty trees. Suppose the smallest tree that we can represent is a one leaf or one node, right? So then the minimum substructure of this tree would be what? Like all trees of one node would be the minimum substructure. But there's an infinite number of them, or at least there's one tree for every element in the base field, right? If you have a tree of A, there's going to be one tree for every element of A. So this is how we go through like this. I just say, okay, just let T be a leaf of X. And you can even say let X be like an arbitrary element from A. But that's sort of like implied by saying this. I'm just saying let T be any leaf X, which is type tree. So one of an infinite many of stuff. And we're just going to go through and map by applying the definition, right? So if I map G.H to this leaf, according to my functor rule, you go into the structure and you apply G.H to the inside of the leaf. And again, I'm being very specific here. Like by line 4, I'm applying F map G.H. Then I can unpack all of the compositions, like using the composition rules. Then I can unapply F map. Then I can unapply, first I can unapply F map G, then I can unapply F map H, which is your favorite proof strategy. Then I can use composition rules to sort of like get rid of this one and make a composition. And therefore, proposition is true for leaf X for any leaf X tree. And again, this is the base case, right? So this is the trivial case. Now very quickly, let's go through the other one. The inductive case. So let T be an arbitrary tree, right? I'm going to say it. So because every tree has to like pattern match against this, right? It has to be comprised of a possibly empty left tree, a possibly empty right tree, and X. So I guess in this case, yeah, possibly. Okay, so a tree is something that's either a left tree or a node, a value, and either a right tree or a node. Okay, and presume the induction hypothesis for PLT and PRT. That's why I don't want you to repeat the statement, because it would be very long. Right? So I'm just saying, let T be this and presume that the proposition holds for the left tree and the right tree. Right? That's the induction hypothesis. And now we have to start unpacking this. So if I'm going to F map G.H to T, now I'm going to run out of room, so I'm not going to be able to justify. But part of your homework, go in and justify each of these lines, right? So this one is just sort of function definition. This one is just unpacking T to like what it says I'm letting it equal. So I guess that's just by assumption. Oh no, I did put the, great, okay. The next thing we have to do is actually like apply the definition of F map to get this inside. So that's what's happening here. So F map G.H to this node is F mapping G.H to the left tree, to the right tree, and then just applying it to the value of the node. So by line 5, we get apply G.H. Then this comes out. And then because I assumed the predicate is true for the left and right tree, I can take this, and I can take this, and then I can use the induction hypothesis to get this and this. And by composition rules, I get that. Like I'm going through this very quickly. You're going to have to take a look at yourself, which is equal to this by unapplying the F map, which is equal to this by unapplying the F map of H, which is equal to this by composition rules, which is equal to this by definition, and therefore PT, and therefore by structural induction PT for every T tree A. I know I went over that very quickly. You're going to have to look at this much more carefully. I'll have to fix that data type. But this is basically like the strategy, right? You set up an induction structurally, which is a little bit different but very familiar, And then you're restricted to just applying and unapplying sort of the definition of the functor that you're working with and these composition rules. Right? And it's the magic really comes in these unapplications. And what my esteemed colleague there said is how you do it, right? You start with the left-hand side and the right-hand side, and you work it down until both things are equal. But then the final thing you have to do is take one of those things and like sort of reverse it and connect it. Because I don't want to read two things and have them connect. I want to have one thing that traverses from left to right.
So it's basically always apply inductive hypothesis, unapply G, unapply F, and then some composition rules in between too.
Well, it's sort of like arbitrary amounts of on applications, and definitions. Utilize the induction hypothesis, and then do an arbitrary amount of applications, on applications, and definitions. Yeah, it's going to be easier than it seems when you like actually start engaging with this. Okay, so let's take a 10-minute break before we move into applicatives, which are a generalization of functors, which are themselves a generalizations of maps. So 10 minutes, and we'll come back. Thank you for that. Or I could have talked about Pekin for like the rest of this, and the fact that we have a French sector in Canada. And okay, so we've taken functions and we've deduced higher order patterns from them called maps. Then we've deduced a higher order pattern than that called functors. And now we want to continue going up the chain of generalizations to generalize functors themselves, to applicatives, which we're going to generalize once more to monads. So applicatives really aren't used that often. Asides is sort of like a stepping stone to get to monads. But nonetheless, like there are cases where like applicatives are quite useful. Exceptional programming, not to say like programming that's good, but like programming that throws exceptions. Like I've had you work a little bit with the maybe and either data type, and you should have discovered that working with it is a little bit cumbersome and annoying, right? Doing all the pattern matches in and out. Applicatives is the tool that like solves that, right? It's going to let us handle exceptions really cleanly. It's essentially the only reason I like taught you about maybe and either. So like applicatives would land as something that is useful. So it's going to be a very same lecture to like the one we just had, where I'm just going to show you what an applicative definition is and what rules they have to satisfy. And we're just going to do like a couple proofs. You definitely need to know how to use functors and applicatives to be successful on your exam. Like there's definitely at least a couple questions that say evaluate this and there's an applicative in it. Okay? So you need to know, the default behavior of list applicative in Haskell, which is really bizarre. It's not the one that we would think that it would be. But in any case, I'm getting ahead of myself. It is natural to generalize functors themselves. For instance, we can do the following maps. But what about, I don't know why it takes so long. Okay, so I want to, like, I could map a univariate function to one list. But like, what happens if I want to map like a bivariate function to two lists? Like, why can't I have a structure preserving operation that does that? Right, that takes two lists of length 3 and returns another list of length 3 with a bivariate function. That should be okay. Why can't I do something like this, right? Like given 3 lists of length 3, why can't I like give it a trivariate function that like gives me another list of length 3? So this is something like zip width, if you've ever seen zip width. So it's like applicatives are sort of like the generalization of zip width in some way. But this is the motivation. Like, I want to be able to map more than univariate functions, and that seems like a very sensible desire, right, to want to do stuff like this. Okay, so what's one option for doing this? Well, so if we had a functor that did univariate functions and did structure preserving operations using them, I could have like an fmap2 that did this and an fmap3 that did that. What's the problem with this approach? well, like when do I stop? Is like fmap 10 million okay? Is like do I need fmap 10 million and one? Like, how do I actually like write all of those things down? Am I gonna have some enormous file where like I've defined, like that would be ugly. It's totally contrary to like Haskell's principles of like defining higher order patterns, but still worth mentioning that that would be one of the options. I actually do think there is an fmap 2 and 3 in the system up to like a certain number, if I remember properly. I forget what it's called. I'll have to look, but I'm pretty sure something like this is in the system. I just forget. Yeah. Was it zip? Oops, maybe not zip 12. Nope. Zip 3? Oh, there's zip 3. Is there zip 4? Well, there's a zip and a zip 3. Anyways, there's something in Haskell which is define these sequence of zips with like a lot of numbers, and I think there's one for each number less than the 2 to the power of 64, but I forget which one it was. It doesn't really matter. So in any case, for this one, if we had functors defined like this, I could say, okay, well, fmap this univariate function over just 1 to get just 2. But I could also say fmap this bivariate function, like fmap addition over just 1, just 2 to get just 3. Like, this is highly desirable behavior, right? Because otherwise, in order to add two just together, we would have to do like a bunch of pattern matching, and there'd be at least 3 cases because of like the 2 nothing cases. This would even multiply the number of base cases we had to write by 2, right? And that would work, right, if we had the following fmaps. The other amazing thing that this does, which I didn't put in here, but is it on the next slide? Is that if one of those things in there is nothing, the whole thing becomes nothing. Right? So it's sort of like lifting the error through. Right? It's sort of handling exceptions for us. I have some slides subsequent to this, but just looking at this, we can agree. If we could get Haskell to do this, this would be highly desirable. Yeah?
How does one nothing make that whole thing? I thought it would just give an error, but why does it do nothing?
Nothing is the error.
Yes. Yeah, because you can't add 2 just together, so it just says.
Well, no, if I had like just 1, nothing, just... Remember, this is something that should work over the maybe data type. Just 1 is from the maybe data type. So here I'd also have to, this fmap would have to work over nothing as well. Right? So in fact, it already does work over nothing. So plus 1 over just 2 is this. Plus 1 over nothing is nothing. Because that's how we define the functor. Right? Okay? And, well, I'll show you then.
It's an instance.
Like we have an instance of... So maybe is an instance of the functor class because it provides an fmap. And the definition of that fmap says mapping on nothing just gives you nothing. And we're going to define these sort of higher order fmaps so that it does the same thing. So that if any of these branches returns nothing, the whole thing will just return nothing. And that is really helpful because otherwise to do something like this, I think would require at least 8 pattern matches. Right? Or at least 1 pattern match for every instance of nothing in every position. So that's at least 3, right? And then 4 for the general case. But in any case, why is this approach insufficient? Each fmap k would have to be hard-coded. There are an infinite number of fmaps. So by those 2 things alone, like we're just going to abandon it. Okay, so these applicatives are going to be the generalization of that fmap. And it looks like this. So to be an instance of an applicative, you first have to be a functor. Okay, so you can't be an applicative without being a functor. So that's what this means, right? In order to be an applicative of f, you have to be a functor already. Okay, so once you're an applicative, what do you automatically get access to? Mapped, right? Essentially. You get access to fmap, right? So if you wanted to use fmap to define your applicative, that's fine. Right, because you have to assume the functor exists. We have to define 2 functions in this functor. One called pure, which basically is the thing that gets you into the structure. Right, given A, wrap it around, and I'll show you why that is going to be useful. And this is what we have to define for an applicative. And this is kind of weird. Okay, so we have some structure F, and I want to make an operation from FA to FB. So I want to make some structure-preserving operation from FA to FB. But the operation itself is going to be inside the structure. Right? This only differs from map in one way, and that's the fact that F is here, right? That the structure is wrapping the transformation itself. These are the laws that an applicative has to satisfy. Pure of ID applicatively mapped to X is X. Pure of Gx is equal to pure G applicatively mapped to pure X. X applicatively mapped to pure Y is equal to pure, okay, this is kind of funny, Y is fixed, and that's going to be the input to a function, which is the input. Right, so this is kind of saying, like, I think I have a way to express, this is equivalent to $y. Right? Instead of giving you the input to the function, I'm giving you a function, and then you're going to put input in it. This effectively means when we learn about monads and sequencing, this sort of is expressing the fact that it doesn't matter which branch is evaluated first. But it won't make sense until we start doing monads. But in any case, it's still one of the laws that you have to satisfy. And this one, which is basically saying we can associate to the right, because this is default left associative. So this is just saying the applicative is associative, right? It doesn't matter how we bracket. Is the question, or your arm just tired? Tired, all right. Okay, so here's a corollary. G mapped to X is the same thing as pure G applicatively mapped to X. So this is called the applicative form, and I'll show you what that means on the next slide after this. So here's how we could define an applicative for maybe. This is the default one that's defined by Haskell. How do I get inside the structure? Well, that's just applying jest to it. So that pure is just going to be jest. And then here it's going to say nothing applicatively mapped to anything is nothing. Just G, right? So that's there's the mapping in there. Applicatively mapped to, when you have something from the maybe data type, it is often useful to name your variable prepended with an M. So this is like a maybe X, right? This is maybe X. So just G applicatively mapped to maybe X is G F mapped to maybe X. So sort of this is the one that you have to remember. To go from something with structure and the function, it's just replacing the applicative with the map instead. Okay, so we'll go over some examples here. Will this work? Will this do anything? What does this evaluate to? These are like very similar to questions on your exam. Does it type properly? That's fine. This is an infix operator. It's like saying plus, plus, plus. Well, what's the first thing have to be? What does this have to be? Well, yes, so what's this going to be? This is important, right? So I'm saying that I'm applying this operation to these two things here. And this operation has this form. So will this type properly? Does plus have the type? Is it a maybe over A to B? No. So that one's just an error. How do I fix it? Okay, like this. If I say just plus, now plus is inside the structure. Now it has that F there. And that gives you just 3. Right? So this is built into the system, right? You could type into the system that statement and we'll give you back just 3. So this is a quick way of adding just types. There are alternate ways that you can do this, right? I can say pure plus, right? Because pure is just the thing that gets you into the structure in the first place. And that's why we define it, right? It's just so that we don't have to search for the particular structure, right? Because this should work over this would work on an either data type, and I don't want to have to sort of change this with left. It's better to use pure. So that will work. This will also work, right? Because if I take that first statement, by definition, it's just equal to this. So you may see this is very commonly written. This is called applicative form, where if you want to do like a sequence of applicatives, the first one is just the F map, right? Because this is going to return something strange by which you can map that plus over. But in any case, I just need you to be able to understand statements like this, right? Which is fine, but you need to be aware of like how the built-in functors and applicatives work for the common data types that we use, like maybe, either, and list. Okay? So this is a little bit, you're going to have to play with these. So now I should be able to do something like this, right? So I'm going to apply pure, a function that takes 3 variables and sums them to like 3 jests, and you get just 6. Right, that would be tough to implement without an applicative. Well, it wouldn't be tough, it'd be maybe messy. I can say pure, take these 3 variables and make a list, right, of those 3 variables and get something like that. But see, it's still structure preserving. Right? We went from just to just. I can say pure, take these 3 variables and see if like the product of the first 2 is bigger than the third. And we get just false. Here are the applicative laws. So let's try to do some of them. Remember, you may have to return to these and stare at them a little bit for them to make sense. But here's the proof for maybe. So I need to prove that applicatively mapping the pure identity function over x gives you x back. So let's just go through this. So pure ID applicatively mapped to x is just ID applicative x, right? That's just me applying pure, like, by definition. That's what pure is going to do. Then this becomes the identity function f mapped to x, right? That's by definition of application. At this point, if x is of the maybe data type, it's either nothing or just something. I'll call it x prime. And in either case, what do you get if you put, if you map the identity over nothing by definition? Nothing. And what happens if you map the identity over just x prime? Just x prime. So in either case, right, it's equal to x or equal to x. So both by definition of and applying functor, the result follows. So here's the base. Actually, this is not a base case. This is just. So this is an induction. This is just straightforward deduction. You're not always going to need induction to do these things. Pure distributes over normal function application. That is, pure preserves function application. That's basically an English statement describing what happens here. So let's just go through the proof for this for the maybe applicative. So proof for maybe. So pure of g applied to x, or pure of x applied to, pure of g applied to x, that is the correct way of saying that, is just g applied to x by applying pure, is just g maps to just x by unapplying this. Right? I can go from here to here by an unapplication. So in order to understand these unapplies, just ask if you reverse it. If I apply this and move up, does that make sense? So do you get how I can go from here to here by applying the F map? Right? So you should be able to read given this proof, you can swap every apply to unapply and unapply to apply and then go backwards. And it should also make sense. I can unapply the applicative to get the just back there and to transform this map back into an applicative. And then I can replace these justs with pure, and the result follows, right? I've shown pure of g applied to x is equal to pure g applicatively applied to pure x.
So are you using just because that's like a structure that you've like proven things on?
So I can't ask you to prove laws. I can't ask you to prove an applicative satisfy laws unless I give you the applicative. Right? So I'm saying we looked at the default definition for the maybe applicative, and now I'm just going through and confirming that they satisfy those rules because it's the simplest one. The list applicative is it's not as straightforward as you would expect it to be. Look at, this is the easiest one and they're already kind of messy. Okay, so this is the weird one, and this is what Hutton has to say about this. When an effectful function, that's a function that has an effect, we're going to learn how to sequence stuff next week, is applied to a pure argument, the order in which we evaluate the two components doesn't matter. I can't really say it better than that. This may not be meaningful at this point because we haven't talked about sequencing actions, but these applicatives are going to let us sequence stuff. We're going to sort of shoehorn back. This is all building the technology required to implement do that you've been using sometimes. Note this, right? Take G to GY is equivalent to $y. So maybe you may understand $y. It's just basically saying, give me a function and then put y in it, right? But the y is the thing that's static. So you can always make this type of change if you want to understand that. Okay, so we're going to prove this applicative law 3 for maybe. And when you're using the maybe data type, you're going to have to do branching, right? Because you have to do two proofs, like one assuming x is nothing and one assuming that it's not nothing. So I usually say assume x is like just x prime, right, to indicate that it's not nothing. So just be mindful of that, especially when the branching can start, like you have branches with branches. You have to sort of be clever about using without loss of generalities and stuff like that. Okay, so note that we have this equivalence. So I'm just going to write it using the equivalence. So that's the statement that we have to prove. And I'm just going to walk through it. So pure of apply y, applicatively applied to just x prime, is equal to this. So all I've done is remove this pure and swap this out with a map, because that's what it means to apply this. Then I just apply the map, right? So this goes inside, right? So we have x prime goes in to here. So this will become x prime evaluated at y. Then I can unapply the map to get x prime out, right? Because x prime is a function that we have. So just go backwards, right? What does it mean to do this, right? You get that. Yeah? If this was an f, I don't think people would be, right? So f mapped to just y would be just fy. So it's the same thing here. I can unapply the applicative, which means this gets its decoration back, its structure, and that map turns to an applicative. This is by assumption, because I've said just of x prime is equal to x, which is equal to x applicatively applied to pure y, because that's all pure does is apply that just, which gets us the desired result. So notice no induction was required here. You're not always going to be using induction, right? Because for one, maybe it doesn't have substructure, right? It's not a recursively defined data type. It's either nothing or the other thing. There's another law. Basically, this is saying associativity. How much time do we have left? 10 minutes? I don't know if I necessarily want to go through this very slowly. Okay, so if I wanted to prove this properly, this would throw a ton of cases, right? Because each of those things can be either nothing or not nothing. So what I'm going to do is I'm just going to say, let's assume all of them are not nothing. Like we'll do that case where everything is a just. Now in homework, I'm not going to ask you this, but if you were to do this later in like other classes or in research, the appropriate thing to do here would be to say, I'm going to make one of them nothing, observe the following symmetry properties, and then like the proof that I did for nothing should apply in a similar way to the other two. It's a phrase called without loss of generality. Have you used it before? That's with respect to. W log would be without loss of generality. You got to be really careful when using it because you have to be careful that you actually do have without loss of generality. So it's I don't think you guys have the I don't want to give you this power yet to use Y-log, but I won't give you questions that require it. Without loss of generality, the solution. Okay, so we need to go from here, and we need to show that we can bracket this on the right, since it's default left associative. I'll just go through quickly. So again, I'm just, so this is the question that I was thinking of, where I didn't provide the justification. I would like you to go in, and for each line, give the justification. So the first one's free, right? The first one, all I did was just apply what pure meant to get this just. This one, I'm just utilizing the associativity rules, right? Because it's left associative. Now I can utilize the composition rules, right? To say, what is this doing? Do my brackets even match? I went through this last night very carefully. Is this still correct? What did I do? Oh, yes, I'm just getting...
You combine just dot and just x prime together.
Oh, yes, I actually just conducted this. Right, so yeah, maybe I should have put a bracket here inside. Oh, I guess that's what that dollar sign is for. Yeah, I shouldn't have used that dollar sign. Okay, but it's correct, right? That's the important thing. So I combine this into this using the rules of applicatives, which gives me this. I'm just moving now this y prime inside as well. And now I imagine I'm going to move this prime inside as well, which is this by my composition rules, which is this by unapplying the applicative, which is this by unapplying the applicative, which is this by definition or by assumption, as desired. Okay? So you're gonna have to go through these at home line by line to make sure. I've skipped a bunch of steps in here too. You may want to fill it out because I had to fit it on one slide. Exceptional programming. So notice the following desirable behaviors when mixing applicatives with exceptions. And this is really important, right? So here's a function which adds 3 numbers together. So I should be able to say pure add them to just 1, just 2, just 3. We're going to get just 6. But what about this? Right? That is really desirable behavior, right? This one line handled all of like the branching. Right? In fact, I can move this nothing anywhere that I want, and it's going to handle it like that. So I believe that the exorcism problems this week aren't new exorcism problems. Like I want you to go back and resolve all of the problems that you did with maybe and just and use the applicative instead. You should be able to like really simplify your work now by using some of these higher order patterns. Like I know was it last week that you had all the jests and maybes, or was that the week before? I'm kind of confused now because we had the off week. Okay, so the last teaching week, you did a bunch of stuff with just and maybes. Try to do it again now using these applicatives instead. The list applicative. So at the beginning of the class, I said, wouldn't it be great if we could like generalize map to zip with? Now you would think that the applicative for list would do exactly that, right? Would basically just do a zip with. It's not the case. For historic reasons, this is the list applicative in Haskell. So this is not too surprising that to get structure on X, you just put brackets around it. You make it a list. Okay, that I understand. This is a little bit different. So they're saying if G's, and so G's is a list of functions, and then you give me a list of A, and then I'm going to generate this list, right? It's all the ways I can apply functions from this list to all of the members of the second list. Okay? You have that in your mind? Because I'm going to do some examples now. What's this? So what does pure do that plus 1 for this list applicative? Well, makes it a list, right? So it's a list of one function. So I'm saying that one function is going to be applied to like every member of the list. 2, 3, 4. Okay. What about this one?
What happens to the just? Pure? Oh, 'cause you
No, pure is different now. The new structure is list, right? We're different applicative. Yeah. So I'm going to apply one function to all draws from 1 and 2. 3. Right? Good. Okay. What about this one? And this is the one that I'd really want to be like 6, 8 if it was like really my applicative.
4, 5, 5, 6.
Yeah. You added, I think, but you should have multiplied. But yeah. Yeah. So it's like apply everything from apply every function in the list of functions. So far that's just multiplication. And apply that to like all the pairs I can draw out from, right, 1, 2, and 3, 4, right? So this is 1 times 3, 1 times 4, 2 times 3, 2 times 4. So last year I gave a problem about, do you guys know what the Cartesian product is? It's all pairs or triplets that you can generate by like A cross B cross C. So I gave this as a question last year to my Comp 3400 class, and that was the one they all cheated on. And how do you think they cheated? It was the very first assignment. Well, of course they Googled it, right? But this is the answer they gave. Right? What is this going to give? You can use list comprehension, but I barred it, right? I barred list comprehension, so they used this instead, right? The same way that I barred like map, but then everyone used functors, right? Or fmap, right? They went much higher up the chain than I anticipated them doing. But yeah, what would this give? So remember, that's the constructor. Like that, this is a function that given two things will create a pair. I'm saying apply that to every sort of tuple that you can get from 1, 2, 3, 4. So that's pretty much what you get. And it even generalizes now, right, to do this. So there are clever ways that you can use this applicative for lists, but it does not act like zip with, which is the thing that like you would expect it to do, huh?
Structure preserving? Like, when you're on like line.
I never said applicatives were structure preserving, right?
I thought they were just better functors.
No, there's like a generalization of the functor, right? Yeah, it's like, yeah, it's more, right? It like you end up in the same structure, but it's not structure preserved, right? Okay. We're out of time, so okay, this is just again reasserting that you can replace like the first thing with a map if you want, so you can read through that. Here's an exercise that I want you to do. This is not going to be your homework. It's just an exercise. I want you to write an applicative for lists that does zip lists, that like zips the lists, right? The way that we would normally think that it should work. Okay, however, there is no way to override the built-in list applicative. Right? So just put a decorator over the list, right? Just create something called zip list and decorate it with Z. Okay, and write me a functor and applicative for this zip list whose applicative does the thing that we imagine it should do. That is do a zip with to the length of the smallest list. And then go ahead and prove whatever you want. Okay? So next week we're going to talk about monads and I/O. Oh, when I say next week, I just always put teaching in front of that. Next teaching week, right? Next time we meet, yeah, in a fortnight. Okay? Work on your assignments. It's my objective this week to have the Gradescope tests written so you can start going and putting your stuff on the Gradescope. I just have to write some property tests. All right, Chad, have a good one. A boot, yes, go in a boot. Thanks, guys.